want you to imagine that you have an eraser on your table, or maybe you have an eraser. You can give it a shot here. But go ahead and slide that eraser across the table. And you should feel the force of friction working against your attempt to pull this eraser across the table. And then if you apply a little bit of force downward as you apply a force horizontally, hopefully you see or you feel that the force of friction is greater. It's harder to move it horizontally when you push down. Now, that doesn't exactly make sense with what we have talked about with forces, because those forces don't point in the same direction. So why do they affect each other? Well, it's because that downward push is affecting a force that is horizontal. It's affecting the frictional force. And so by increasing the normal force, we changed the frictional force. If we just look at the vertical forces in the first situation, everything was balanced. Normal equaled the gravitational force. But if we look at the second situation, the gravitational force didn't change. My pink arrow stays the same length. But the downward blue push by the hand causes the normal force to have to increase. The normal force just responds to whatever we are doing. And so that extra normal force actually causes the force of friction to increase. That's sort of the big takeaway from that quick thought experiment. And we'll come back to that in a second and see how this affects the formula that we're going to build for friction. All right, now let's change the object itself, and let's think about something that's not so soft, not so grippy to the table. Imagine just a wood block being slid across the same table. So what would happen there? Would there seem like there's more friction or less friction? Is it harder to pull? Is it easier to pull? Okay, so hopefully you'll notice here that the greater or that change in material made the force of friction be smaller. It was easier to slide the wood block across the table than the eraser. So the amount of interaction between those materials, between the eraser and the table, or between the wood block and the table, has to be taken into account. And so what we'll use here is something called the coefficient of friction. It's a number that describes the interaction. So the greater the value of the coefficient of friction, the more interaction there is, the more sort of grip between the two materials. And the lower value of coefficient of friction, the more easily things slide past each other. The symbol we use is a Greek letter. It looks kind of like a U with a little tail in front. This is pronounced mu. And again, it's a Greek letter. It just stands for the number, a number that represents sort of how much friction there is, but not exactly that, but just how hard it is to slide something past another surface. So a little bit more about that. That number mu is always going to be something that is between 0 and 1, except for very rare situations. So that helps you decide whether your answers are coming out logically. Here are some common values of mu just for your reference. You don't need to write these down. But something like wood on wood, like we were just looking at, that would be 0.2 as a typical value of mu. And then if it was more like rubber or like an eraser type thing, it's going to be a little bit bigger of a value of mu. If that, you think about car tires on wet concrete versus dry concrete, things are much more slippery on the wet concrete. And so you can see how the value of mu, 0.25, is significantly smaller than the value on dry concrete of 0.8. And then things like ice, sliding across ice, real easy to slide, so very, very low value of mu. And then the joints in your body, luckily, have incredibly low values of mu, low coefficients of friction, virtually 0. So what we want to notice from this again is that increasing this thing called the coefficient of friction also increases the frictional force. So if we put these two ideas together, we should be able to come up with a formula that relates friction to these two concepts. And this is the key formula. Make sure you jot this down. The force of friction can be calculated by taking the value of mu and multiplying by the normal force. Well, there's actually a couple different types of friction, and you saw that in some of the earlier slides where there was like a little k next to that mu. That is a distinction between what's called kinetic friction, which is what we almost entirely talk about in class, at least in terms of calculations. Kinetic friction is when the surfaces are actually sliding past each other. But then there's also something called static friction. Static friction is the friction where the surfaces don't slide or don't slip. Examples of where you see that is when we talk about how you need friction in order to walk. It's your shoes not sliding along the floor that sort of represents that friction. And so that would be a static friction idea. Or if you park your car on an incline and the car does not slide down, it's because of the friction between your car tires and the road. But that's a static friction idea because they're not actually slipping relative to each other. Turns out the calculations are a little trickier with that. It is something that we deal with in the AP Physics class. Our class mainly talks about kinetic friction and only calculates really kinetic friction values.
So in order to calculate the force of friction, we're going to need the normal force because the force of friction is mu times the normal force. Let's take a look at a force diagram so that we can imagine all the different forces. Our block is sliding across the floor and there's friction. It doesn't say it's being pushed, but we do need to have a sense of which direction it's moving. So let's assume it's moving to the right, and that means our frictional force would push to the left. And then there would be the gravitational force, F of g equals m times g. And then the normal force, and since it's moving horizontally, we would know that those two are equal to each other. So to find the normal force, I just really need to calculate the frictional force, which is mg. And since our mass is 6 kilograms, that means the normal force would be 60 newtons, 10 newtons per every kilogram. And so then finishing this off, our frictional force would be this unitless value, 0.2 is the mu, and then times 60 newtons, and so that would give us 12 newtons as our frictional force. Problem 2 takes us a step further. We are being asked to find the acceleration of the block. And so what we'll do here is we will first think about the frictional force, but then we'll also think about just F equals ma as well. So let's sketch a force diagram and assume it's moving to the right again. Again, that's kind of how my brain works. So we have an applied force. So I'll just call it F sub p as a shortcut here, and that is 16 newtons. And then we're pushing this 4 kilogram block horizontally across the floor. It mentions friction and it says it's going to accelerate, so I'm going to assume that the acceleration is positive and make my frictional force smaller, but of course it could be that it's bigger and it slows down. I just usually assume the positive acceleration, and then if my answer comes out negative, I just know it's slowing. I would also have the gravitational force, and I would have the normal force, and then because it's not moving, these two forces are equal. So I'll start by finding the normal force. It would be balanced with the gravitational force, which again is going to be the mass times 10 newtons per kilogram. So 40 newtons. And then I could calculate the force of friction first, but I'm just going to go ahead and do this all sort of in one big equation. So Newton's second law says that the sum of the forces is equal to m times a. And from my picture, I can pick off what the sum of the forces are. I'm looking for any force that helps the motion minus whatever force works against the motion. And so I'm just going to write a general statement first. This is a good habit to get into so I can handle any sort of situation. My applied force minus my frictional force equals mass times acceleration. And then I'll go ahead and also substitute in that frictional forces can be calculated by taking mu times the normal force. Okay, so now I have a very general statement based on my picture. I'll go ahead and plug in all the values I know. So the pulling force was 16, the applied force. My mu is 0.3, and the normal force was 40. That will equal my mass is in kilograms, times my acceleration. Now I'll do a little bit of algebra. So 16 minus 12 equals 4 times a, and 16 minus 12 is 4. And so my acceleration is 1 meter per second squared. All right, and in my last question, I have a block that is again moving across a floor. This time I'm told that it's moving at constant speed. Recall that what that means when something moves at constant speed is that the force forward, which in this case is an applied force of 3 newtons, that has to have the same value as the force backwards, which in this case is a frictional force. And then I would also know that the gravitational force down would equal the normal force up, also equal, although different equals. And so I can do kind of the way I have been doing in the past here, that the normal force is the same as the gravitational force, which would be 2 kilograms times 10 newtons per kilogram, or 20 newtons. And then I can also say that these forces would have to be equal. So 2 ways I could do it. I could sort of be very formal, and I could say that the sum of the forces equals ma, but that because it's at a constant speed, there is no acceleration. So I could set it up that way, or I could just notice that the forces are balanced, and just sort of use that idea. And so my frictional force has to equal my applied force. And my frictional force is, of course, mu times the normal force. And so at this point then, I have everything I need. I can plug in what I'm looking for. Mu is my unknown, the coefficient of friction. It's kinetic because there is motion in the problem. The normal force is 20. And then my applied force in this case is 3. And so mu would equal 3 divided by 20, which is 0.15. There are no units on the value of mu. The 20 is in newtons and the 3 is in newtons. And so those 2 units cancel out, and I'm left with a value only, no units on this particular answer. One thing to note before we close off here, even though you were given this value of the speed, it does not affect the answer. All we needed to know was that the speed was constant. The problem is not actually asking how fast it's moving or dealing with that. It's really just dealing with the fact that it is a constant speed, and so the forces are balanced left and right.